In this video we're going to look at redox titrations. So redox titrations are put into the transition elements topic, and that's because the colour changes that are associated with reactions of transition elements, we can use these colour changes to effectively measure endpoints in titrations. So once you know the endpoint, you can then use these values to measure molar quantities involved in the reactions. So just like in an acid-base titration, we would use an indicator to tell us when all of the acid or base has been neutralised. What we're going to do in redox titrations is we're going to use the colour change, and that's going to tell us when all of a particular transition metal ion has been reacted. And just a reminder for you why these are known as redox titrations, and that's because the reactions that we're going to look at involve reduction and oxidation processes. So there's no better place to start than the classic redox titration, and that is the reaction between the MnO4- ion, so that's the manganate 7 ion, and iron 2+ ions. So I've got both of the half equations there for you. Now you may have to write these from scratch in the exam, or you may be supplied with them and then you're going to have to do something with them. So I've got writing half equations on a different video, so if you're a bit rusty on that, then have a look at that one. But let's suppose you've written your two half equations. Where do we go from here? So what we need to do is we need to get the electrons to cancel out. So you can see we've got 5 electrons in this half equation, and we've got only 1 involved in this one. So if we multiply this half equation by 5, and then we're going to add it to this half equation, we'll have 5 electrons on the left hand side and 5 electrons on the right hand side, and they will just cancel out. And there's your overall equation, and you can see that I haven't bothered to write the 5 electrons on each side because they will obviously cancel out. So the important aspect of this redox reaction is the fact that 1 mole of manganate 7 ions will react with 5 moles of iron 2+ ions, and that's going to be very important when we go on to our calculations, which we're going to look at now. Apologies for my crude diagrams here, but hopefully this will get the message across. So there's the overall equation again, squeezed over on the left there. If you were doing this titration, you would typically have a solution of manganate 7 ions in your burette. So this would probably be in the form of KMnO4, potassium manganate 7. And you can see there that that's purple in colour. That's why I've chosen the purple pen. And in the conical flask you would have your solution of iron 2+ with some aqueous acid in there to provide these acid conditions. So keep an eye on the colours here. So remember, this is purple. Now, when the MnO4- ions react with the Fe2+ ions, the iron 2+ is oxidised to iron 3+, and the MnO4- ion, well, the Mn is reduced from +7 down to +2. Now this is so pale pink, it's effectively colourless. Okay, so it's not technically colourless, it's very, very pale pink. Now, if you think about it, as long as there's some iron 2+ in this solution, this has got something to react with. As soon as all the iron 2+ is reacted, then your next drop of MnO4- from the burette has got nothing to react with, and so it won't go colourless, it will stay purple. So the end point of this titration would be when you see your first permanent pink sort of tinge of colour. So you swirl in the flask and it's not going colourless anymore, it's staying pink. that means the reaction's finished. And you would obviously note that burette reading, and that would be your titer or end point. So what we're going to do now is we're going to look at some examples of redox titrations. The first one that I'm going to look at, this one on the board now, is probably one of the simpler types of calculations. So I'll do different types. The trouble is there's so many different calculations out there. I could have my own YouTube channel just on redox titrations. So unfortunately I'm not going to have time to cover every possible type of reaction, but I'm sure that this will give you an idea of how to tackle this type of question. So you can see there, this type is all about calculating the concentration of a solution. So we've got a piece of pure iron wire, we're given its mass, it was reacted with aqueous acid so that all the iron atoms are converted to iron 2+ ions, and then the resulting solution was titrated with potassium manganate 7 solution, and it needed 26.2 cm³ of that. And we have to calculate the concentration of that KMnO4 solution. And there's a condition there, we have to give our answer to 3 significant figures as well. So the first thing I'm going to do is I'm going to try and help you visualise what's going on in that question. I'm always saying to my students, draw a little sketch, draw a little picture of what's going on in the steps, and that will hopefully help you to visualise what's going on. So there's the first step. We've got the known mass of iron wire, and we've poured some aqueous acid in there, and what's happened, that's turned into a solution of iron 2+, and obviously we've got the H+ ions from the acid that we need for that redox reaction. And then the titration takes place. So we've got our burette filled with KMnO4 solution, which contains this MnO4- ion, which you saw in the redox equation, and we are told that we need 26.2 cm³ of that. So we'll start going through the steps involved in the calculation now. So the first step involves the iron wire that's inside this flask. So we know the mass of the iron wire. It's reacted with aqueous acid, so in other words H+ ions, and the iron atoms are turned into iron 2+ ions. The important thing here is every mole of iron would form the same number of moles of Fe2+ ions. So we've got enough information here to calculate the moles of iron, because we know the mass, and obviously we know the MR from our data sheets. And so you can see there, mass over MR, the moles of Fe are that many, and from this little conversation we had, that's also the moles of Fe2+. So we know at this point the moles of iron 2+ that are inside that flask. So we're going to bring the redox equation into play now. So we know the moles of iron 2+, we know this quantity here. We want to find out how many moles of MnO4- ions were present in this required volume from the titration, is 26.2 cm³. So if we look at the mole ratio, that's a 1:5 ratio, so therefore the moles of MnO4- is obviously 1/5 of this, 2.5 times 10 to the -3, and that comes out at 5 times 10 to the -4 moles of MnO4-. And now we know the moles of MnO4- ions, this 5 times 10 to the -4. We know the volume that was required in the titration, this 26.2 cm³. And if you notice there, I've converted it into decimeters cubed because that's what you have to do in calculations involving concentration. And if you divide that by that, you'll get the concentration comes out at 1.91 times 10 to the -2 moles per decimeter cubed. So you can see, hopefully, by visualizing the process, by visualizing the question, you can hopefully make more sense of what's going on. And that will certainly help when they get more complicated than this one, which unfortunately they will. So the next example I've got for you, I'm classing as a calculating the percentage composition, and we are going to do a calculation involving some iron ore. So obviously iron ore contains iron and other things. So you can see on the sheet there we're given a mass of impure iron ore. It's reacted with acid to turn the iron atoms into iron 2 plus ions. The solution produced needed 23.5 cm cubed of that concentration of KMnO4 solution, and we have to calculate the percentage by mass of iron in the ore, and we've got to give our answer to 3 significant figures. And there's a simple visualization of the experiment. So in the first flask we've got the ore and we're pouring that aqueous acid in. That's going to turn the iron atoms in the ore to iron 2 plus ions. So you can see in the second flask we've got the iron 2 plus ions in aqueous solution with some H plus ions, and there's the burette above with the 0.04 moles per decimeter cubed KMnO4 solution, and there's the average titra, 23.5 cm cubed. So you can see I've put the redox equation at the top of the board there, and we need the mole ratio from that between the MnO4 minus and the Fe2 plus. So the first thing we're going to calculate, because we have all the information to do so, is the moles of MnO4 minus. So that's the concentration, 0.04, times the volume in decimeters cubed, 0.0235. So that comes out at 9.4 times 10 to the negative 4. From the mole ratio in the equation, we can see that we need to multiply the moles of MnO4 minus ions by 5 to get the moles of Fe2 plus. So that comes out at 4.7 times 10 to the minus 3. And remember, the Fe2 plus came from the iron atoms in the ore, so that must mean that there's the same number of moles of iron in the ore, so 4.7 times 10 to the minus 3 again. We can convert that into grams, so the mass of iron in the ore is the moles times the MR, 55.8, which comes out at 0.26226. And finally, to turn it into a percentage, we take the mass of iron in the ore, divide that by the total mass of the ore, the 0.402, and multiply by 100. So to 3 significant figures, the answer is 62.4% by mass of iron in the ore.